My screen is visible. Okay,
Yes, sir.
then we will start. Okay, in last lecture, we have discussed about how to plot the equilibrium diagram, and with the help of different types of the cooling curves. Now, with the okay, okay. In last lecture, we have discussed about how to plot the how to plot the equilibrium diagram with the help of the cooling curves, and that method is termed as the thermal analysis method for plotting the equilibrium diagram. And in that, we have seen by taking the example of the copper and nickel alloy, how to plot that equilibrium diagram with the help of by taking the different composition samples and their cooling curves. And after understanding how to plot the equilibrium diagram, we have also tried to understand the concept of the lever rule principle, or you can also call it as a lever arm principle. That lever arm principle is very important as far as your gate examination is concerned. In I think two or three times they have asked questions on that lever rule, how to apply that lever rule. They will provide you one equilibrium diagram with different compositions and temperatures values, and they will ask you to find out the amount of liquid and amount of solid. Okay, that this part we have discussed in the last lecture. Now in this lecture, we are going to discuss the different types of the phase diagrams. Now here, we are going to discuss the types of the phase diagrams depending or for only binary alloys. Okay, these are the as you can see on the screen clearly, there are four types. I have written four types: isomorphous system, layer type system, eutectic system, and partial eutectic system. Now these, there may be number of several phase diagrams types, but these four types are only for binary alloys which are having only two elements. For that binary alloys, generally there will be only four types of the phase diagrams. Now on which basis these types of phase diagrams are determined? So depending on the solubility of the one metal into the another metal in the liquid state and in the solid state, these four types of phase diagrams are categorized, or these four types are made depending on the solubility of one metal into the another metal in the liquid state and in the solid state. Now we will discuss it one by one. I will explain the first type in the isomorphous system. uh, this is the isomorphous system. In the isomorphous system, both metals will be soluble in each other in liquid state as well as in the solid state also. Okay, that type of the system will be termed as the isomorphous system. Okay, I will repeat it again. uh, the system in which both metals are completely soluble in each other in the solid state as well as in the liquid state, that type of system will be termed as the isomorphous system. Then second type is layer type system, when both metals are completely insoluble in each other in liquid state as well as in the solid state. That type of system will be termed as layer type system. Okay, in isomorphous system, metals will be completely soluble in each other in liquid as well as in solid state, and in layer type system, both the metals will be completely insoluble in each other in the liquid state as well as in the solid state also. Now third type is the eutectic system. Now in this eutectic system, metals will be completely soluble in each other in the liquid state and completely insoluble in the solid state. That type of system will be termed as the eutectic system. Okay, metals will be completely soluble in liquid state and completely insoluble in each other in the solid state. Now the fourth type is partial eutectic system. Here just little bit difference between eutectic system and partial eutectic system. In the partial eutectic system, both metals will be completely soluble in liquid state and partially soluble in the solid state. Okay, only small difference is there. That is, in the eutectic system, they are both metals will be completely soluble in liquid state and completely insoluble in the solid state, but in partially eutectic system completely soluble in liquid state and partially soluble in the solid state. Okay, that system will be termed as partially eutectic system. As far as your examination is concerned, in that exam they will ask you one system from these four. Compulsory one question will be there. On the one phase diagram, they will ask you to draw the phase diagram and put some examples for each type, and you have to explain what exactly happening during the cooling of the alloys with the help of the microstructural changes. Okay, that we are going to discuss in the later half of this lecture. Okay, now we will move forward. First we will see isomorphous system and how microstructural changes are occurring in this isomorphous system. Okay, this is the next slide. It is showing the isomorphous system. In that diagram you are seeing the schematic phase diagram of an isomorphous system. Okay, this is the general phase diagram for any isomorphous system. Now, here, first point, already I have told you that these diagrams are often for two metals having complete solubility in the liquid state as well as in the solid state. Now, here, from diagram itself, you can clearly understand that whichever shape you are getting here for that phase diagram is a loop shape. That's why these diagrams are loop type. Generally, isomorphous system, for any isomorphous system, you will get a loop type phase diagram. Now, for examples, you can say that this example already we have seen in the procedure for plotting the equilibrium diagram, that is the copper and nickel. Means this will be completely soluble in the liquid state. Copper and nickel will be completely soluble in each other in liquid state also and in solid state also. Means whenever that alloy will be in liquid state, you will get only a single liquid, and whenever it is in the solid state, you will get only a single solid. Then another example is gold and silver. Okay, in gold and silver, the practical example that gold and silver, gold and copper. If suppose you have mixed some amount of silver in the gold, it cannot be visible. You can see in your gold ornaments they have added some copper or silver material, copper or silver material. Okay, and it will be completely soluble in each other. That's why it is showing only one solid. It will show only one solid, that is gold and silver, then gold and copper. Then another examples are tungsten and vanadium, that is Wv. Then molybdenum and vanadium, then molybdenum and tungsten, molybdenum and titanium, then gold and nickel, and BiSb, that is the Bi means bismuth and Sb is the antimony. Okay, so these are the different examples. One or two examples will be sufficient. You can clearly understand or you can remember this example copper and nickel because we are frequently using that example. Then you can take the examples from your practical life, that is your gold ornaments. It will be having some amount of silver and copper to provide little bit strength in that. Okay, these are the examples for that. Now, here, what will be the microstructural changes you have to explain. Here you can see from that loop, almost if you take any alloy, the changes or your cooling curve nature will be same. As I have taken here one vertical line, one dotted vertical line showing Z% of B. For that I will explain what will exactly happen during the cooling process. Okay, please see that dotted vertical line in that diagram. Dotted vertical line, this diagram. Okay, I will little bit try to zoom it. Is it clearly visible? Please confirm me.
Yes, sir.
Anyone? Azam Sheikh, can you confirm it? Whether that diagram is clearly visible for you, please confirm it.
Yes, sir, it's visible.
Okay, okay. Now I will explain it. Now here, as you can see from this curve is whenever any composition, for any composition, if you take any composition, its cooling transformation curve or microstructural changes will be of same nature. Now I will explain first in short description of this diagram. Here, if you see clearly this point C, here I am highlighting that point C is melting point of this element A, and this point D is melting point of this element B. If you are taking a practical example, you can say that copper and nickel, then this point C will be melting point of copper, and this point D will be melting point of nickel. And on x-axis we are plotting, means from point A to point B, percentage of nickel is increasing. If you take this copper nickel example, or if you are taking this A and B elements, then percentage of B will goes on increasing as you are moving from point A to point B. At point A, this element B will be 0%, and at point B, element B will be 100%. Now if you are able to see this line, the top curve line, here I have given the name liquidus line. Okay, this top line CMD, this line will be termed as liquidus line. Above this line, that metals or alloy will be in the liquid state only. And the line CND, okay, this lower curve CND, I am highlighting, I am moving this cursor here, CND, this line, this is the solidus line. Below this line, your metal or your alloy will be in solid state only. And in between this loop type curve, in between these two lines, your metal or alloy will be in liquid plus solid state. Okay, your metal or alloy will be in the liquid plus solid state. Above liquidus line, metal or alloy will be in the liquid state. Below this solidus line, it will be in the solid state, and in between these two lines, it will be in liquid plus solid state. Okay, now here, this is the description of this diagram. Okay, then after that, you have to consider any one cooling curve. Here I have taken one curve with Z percentage of B. Here I have marked point Z. It is Z percent of B. You can take any composition. You can take 10% B, 20% B. This is just example. You can take any composition, and you have to just explain the whichever microstructural changes are occurring. Here I have marked the points from 1, 2, 3, 4, and 5 like this. Okay. Now I will explain this. That is the cooling of an alloy with the Z percent of B. I have to explain that. You can assume any percentage of that element B, or you can take that 10% of B, 20% of B, like that. Now, please see this dotted vertical line carefully now. From point 1 to 2, from point 1 to 2, here your alloy will be in liquid state only from 1 to 2. Whichever changes are occurring in the temperature, there will not be any change in the phase. Alloy will remain in the liquid phase only. Then when temperature reaches at point 2, solidification process will start. Solidification or freezing of that alloy will start. And when temperature is decreasing below point 2, when temperature is decreasing below this point 2, amount of liquid will decrease and amount of solid will increase. As temperature is falling, solidification is more and more. Then slowly when it reaches at point 4, that solidification process will get completed, means all liquid will get transformed to a solid. During this region 2 to 4, your alloy will be in liquid plus solid. Some amount of liquid will be there and some amount of solid will be there. And below this point 4 up to this point 5, means up to room temperature, this alloy will be in solid state only. Okay, these are the microstructural changes. Means we are having here clearly three regions, that is 1 to 2 in the liquid state, then 2 to 4 that alloy will be in liquid plus solid state, and 4 to 5 that alloy will be in the solid state only. Now these changes are here. Maybe this diagram may not be visible, but just try to understand the microstructural changes. From here A to B is marking is given, it will be only liquid initially. Just see this top diagram. In region this A to B region, only liquid will be there, only liquid will be there. Then in this region B to D, okay, in between this some amount of liquid and some amount of solid will be there, some amount of liquid and some amount of solid. And when temperature reaches at D and below this point D, only solid will be there. Okay, means in this region only liquid will be there. In the middle region, that is liquid plus solid will be there, and at the end only solid will be there. Okay, these are the microstructural changes which are occurring during the cooling. You have to draw this diagram and you have to show the microstructural changes for this region 1 to 2. Draw one circle, and in that you have to show the liquid only. Then 2 to 4, again draw one circle and you have to show the some amount of liquid and some amount of solid, that is the liquid plus solid phase. And for region 4 to 5, the last microstructure will be there and you have to show only solid will be there. Okay, so these are the microstructural changes occurring here. Okay, again I have taken one extra line here, so this much description is sufficient. Then for better understanding of that lever rule, we will try to find out the amount of solid and amount of liquid. It's by taking this point. Okay, I have taken this horizontal line m n. I am highlighting this m n. Okay, this is for the your competitive examination or your gate examination purpose, how to calculate the amount of solid and liquid for given temperature. Suppose they have given one temperature and I have drawn one horizontal line from that temperature, and I got this m and n line. And from given composition, suppose z is the given composition, I drawn a vertical line. Okay, it intersects that mn line at point 3. Now this mn is the tie line, or you can say that this is the lever arm mn, and this point 3 is the fulcrum point. Now I want to calculate at this particular temperature and this particular composition amount of liquid and amount of solid. Now amount of, to calculate the amount of liquid from this side, liquidous line side, take the opposite length of this m3n line. Okay, this mn line, due to this fulcrum point 3, it is divided in two parts, that is line 3m and 3n, and mn is your tie line. Now amount of liquid will be equal to, apply this from this liquidous line point, opposite arm length, that is amount of liquid will be equal to opposite arm length is 3n divided by total arm length is mn. Means amount of liquid will be equal to 3n by mn. Okay, then you will get the amount of liquid by putting the composition values for point m and n that will be provided in the numerical itself. Now to calculate the amount of solid, now you have to apply the Weaver rule from this solidus line side, this side. From this side you have to apply now amount of solid will be equal to opposite arm divided by total arm length, that is 3m divided by mn. From this you will get the amount of solid. Okay, in this way you can apply the rival rule principle for this particular system. For this composition and temperatures value will be provided in the numerical itself. Okay, so this is the description for the isomorphous system. Then you have to consider one cooling curve, and you have to give the some microstructural changes which are occurring there, and you have to write few examples for this system also. Okay, if you are having any doubt, you can ask me. If it is clear, then we will move towards the next point. Please confirm me whether all points are clear from this isomorphous system.
Yes, sir.
Prajwal, can we move forward? Prajwal.
Yes, sir.
Okay, any other person is there? Azam is not replying. Azam Sheikh is there.
Sir, as he's using
Yes, sir, continue.
Okay. You are able to understand everything?
Yes, sir.
Azam. Okay, okay. Any other
No
person?
problem.
Okay, okay. We will continue then. Yash. Yash Gadekar is there.
Yes, sir.
Are you there? Yash. Yash Gadekar.
Hello, sir.
Okay. You are clear about this isomorphous system?
Yes,
Okay,
sir.
okay. Then we will move forward. The next type of the isomorphous system, sorry, next type of the phase diagram is layer type system. Okay. Now, as I have already explained that what is the layer type system. Now here in the layer type system, these diagrams are obtained when two metals are completely insoluble in liquid state as well as in the solid state. Okay, both metals will be completely insoluble in liquid state and completely insoluble in the solid state. Okay, now here, 1 minute. Now here you can take examples of, here I have mentioned some examples: copper molybdenum, then copper tungsten, then silver tungsten, and silver iron. Now very practical example which already you have seen is the silver and iron. If you are having wearing that ornaments made up of silver, and if some amount of iron is added in that, you can clearly, it is clearly visible in the solid state also. Okay, in the previous example, if you are wearing gold ornaments and some amount of silver is added in that gold ornament, you cannot see that silver in that gold ornaments clearly. But if you are wearing the silver ornaments having silver and iron, that silver and iron will be clearly visible. That is the example of the layer type system, that is the silver and iron. Okay, these are these are the practical examples which are available for you in your practical life. For isomorphous system, we have considered here one example. You can see clearly here, gold and silver, gold and copper. Okay, in your gold ornament there may be some amount of silver and copper, but it is not visible in the solid state, as these are completely soluble in each other, and amount of gold is more, you will be able to see only gold in that ornament. And if you are using the ornaments having silver and iron, then in the solid state, that silver and iron will be separately and clearly visible. That is the example of the layer type system, that silver and iron. Then in the same way, silver and tungsten will be visible if tungsten is added. Okay, so these are examples of the layer type system. Now in this layer type system, uh, as this name is given as layer, you can, whenever you are observing the microstructure for that particular alloy, you will be able to find the different layers according to the density of that particular metal. Okay, denser metal will be present at the bottom. Like this, you will be able to see the layers of that different metals. Suppose silver and iron is there, you will able to see the different layer of the silver and different layer of the iron. Their morphology will be different. Okay, morphology or appearance will be different, means they are forming the different layers. That's why this type of systems are termed as layer type of system. Means whenever you are seeing their microstructure or observing their morphology with the help of microscope, you will be able to see the different layers or different horizontal lines and different vertical line structures. That type of structures will be termed as layer type of structure. That due to this name is given as a layer type system. Now the diagram will be like this phase diagram for layer type system will be like this. It is clearly visible on your screen. Now here you can clearly see that I will explain this here this system is shown for alloy consisting of metals A and B, element A and element B. On y-axis temperature is plotted, and on x-axis percentage weight percentage element B, weight percentage of element B is plotted. Means for at point A, B percent will be 0, and at point B, percentage of B is 100%. Means when you are moving from point A to B, percentage of B will be in increasing order. Then this point C, this point C is melting point of element A, and this point F, or you can say this point D, is melting point of element B. Then this line CG, this top horizontal line, this line CG is the liquidus line. Means above this line, metals or alloys will be in the liquid state, and this line DF, this horizontal line DF, is the solidus line. Below this line, alloys or metals will be in the solid state only, and in between this, liquid plus solid state will be there. Okay, this top line CG is the liquidus line, and this middle line DF is the solidus line. Below this solidus line, metals or alloy will be in only solid state, and above this liquidus line, metals or alloy will be in the liquid state only, and in between this, alloy will be in solid plus liquid state. Now as you can see from this diagram here, this diagram is almost uniform throughout. Then you can consider any one curve for explaining the microstructural changes. Here I have considered one curve here by marking or taking the z percentage of B, z percent of B. One curve I have considered here. Now I have to explain, or you have to explain the cooling of this curve with z percent of B. What will be the microstructural changes and how this cooling is occurring? That you have to explain here. Now at point 1, here alloy or alloy is in liquid state. From point 1 to 2, it will remain in the liquid state only. Okay, your alloy will be in the liquid state only. But here you will able to find out two separate liquids. Okay, as these elements are completely insoluble in each other, two different liquids will be clearly visible here in the region 1 to 2. As you have seen in the isomorphous system, as metals are completely soluble, only one liquid is there. But in case of this layer type system, in this region 1 to 2, as these metals are completely insoluble in each other in the liquid state also, that's why you will be able to see two liquids. You have to draw one circle, and you have to show two liquids with different colors, that is liquid A and liquid B, in this region 1 to 2. as temperature is increasing or in decreasing order, there will not be any change in the phase. Means it's only liquid phase will be there in the region 1 to 2. As temperature is dropping here, as we are moving from 1 to 2, liquid phase will be there, and two different liquids will be you can clearly see the two different liquids in this region 1 to 2. And when temperature reaches at point 2, as this is the melting point of element A, this liquid A will get solidified as temperature reaches at point 2. And below this region from 2 to 3, this alloy will be in the solid plus liquid state. As at this point, okay, is there any problem? Ganesh Todkar, is there any problem? Okay, can I continue? Is there any problem? Ganesh Todkar is there?
Yes, sir.
Yes. If you are having any difficulty, you can ask me.
No, no, sir.
Okay,
No.
okay. Then I will continue. Okay, I will repeat this part. For the cooling, now I am explaining the cooling of this curve with Z% of that element B. Or you can consider any percentage here, 10% B, 20% B, 30% B, like this. Now for this, I have marked here points 1 to 2. In this region from 1 to 2, alloy will be in only state will be liquid, but you will able to find out two different liquids as element A and element B are completely insoluble in each other. Then during the cooling, when temperature reaches at point 2, this as this point 2 means this point C is melting point of element A, this liquid A will get solidified at this temperature, and in region 2 to 3 you will be able to see there will be two phases, solid phase plus liquid phase, and solid will be of element A and liquid will be of element B. Then as you are dropping the or temperature is dropping continuously, and when you reaches at point 3, this point 3 means your point D is melting point of your element B. That element, this liquid B will get solidified at point 3, and you will get the mixture of solid A plus solid B. From in this region 3 to 4, continuously there will be only one mixture will be there, that is solid A and B, as these both solids are completely insoluble in each other. In this region 3 to 4, you will get the mixture of two solids, or it will be clearly visible from the microstructures. Two morphologies will be present, or two metals having different appearance will be there, and that structure will be present in the layer form as depending on their densities. Denser metal will present at the bottom, and they will form the layer type structure. That's why this system is termed as the layer type system. Okay, so this is the explanation for this layer type system. Please draw the diagrams for isomorphous system. I will wait for a few minutes and draw the diagram for layer type system also. First, I will wait for a few minutes and draw the diagram for isomorphous system. Please draw it, and after completion of drawing, you can put that in the chat box. If you are having any questions regarding this isomorphous system and layer type system, you can ask me. You have to first explain in these Bose diagrams, you have to explain first nature of the solubility of that both metals in each other in liquid and solid state. Then shape of that phase diagram or equilibrium diagram, few examples. Then you have to consider cooling curves in the different regions. As here curve is uniform, only one cooling curve is sufficient. You have to consider that cooling curve, and you have to explain the cooling curve with the help of microstructures also. For each region you have to draw the microstructures. Okay, please draw that diagram for isomorphous system. Okay. Please draw the microstructural changes also. Means for this isomorphous system in region, first top region 1 to 2, I will explain. For this 1 to 2, there will be liquid. Then 2 to 4, liquid plus solid, and 4 to 5, only solid. Also show that microstructural changes there. Okay, microstructural changes, you have to show that microstructural changes. For first region 1 to 2, only liquid will be there. Now, same microstructure will be this first stage microstructure for layer type system will be, you have to show two liquids here. In this region 1 to 2, two liquids will be there, liquid A and liquid B. You have to name it differently. Now in the center portion, for this here we are having liquid plus solid. There also you have to, same microstructure will be there, liquid plus solid, but you have to name that solid A and liquid B for the layer type system. And at the end portion here we are having only one solid, and for the layer type system we will be having two different solids will be there only, but you have to highlight some one solid by blank portion and one solid by color portion, or you can dark it, and you can show that one solid A and solid B, like that for that layer type system. Okay, two different microstructures you have to show here. This is the layer type system. For 1 to 2 region you have to show two different liquids, and 2 to 3 one solid, and that will be named as solid A, and remaining will be liquid B. And for this 3 to 4 microstructure will be solid A plus solid B, like this. Okay, uh, now in this lecture we have discussed this part. Now the next diagram, next phase diagram is for eutectic system and partial eutectic system. And it will, that eutectic system is having three different regions. As you have seen in this diagram, there is only uh, means that curve is uniform throughout. You have to consider only one cooling curve. But in case of eutectic system, you have to consider three different regions, or three different cooling curves, and you have to explain the cooling of that all three curves, and you have to show the microstructural changes also. And in the partial eutectic system, almost 4 or 5 cooling curves you have to consider, and you have to explain the microstructural changes. So it will take a little bit more time. That's why that part we will see in the next lecture. Okay, if you are having any difficulty in this lecture, you can ask me. If you are having any difficulty, please ask me, or if it is clear, then I will close the lecture. Kindly give reply.
No doubt, sir.
Okay, okay.